All right, so we're going to conclude our discussion about past climate change by taking a deep dive into basically the worst singular event in Earth history. That's the extinction at the Permian-Triassic boundary around 250 million years ago. So this event killed off almost all life on Earth at the time, including many of the so-called Paleozoic fauna, including these little guys over here. These were the dinosaurs before the dinosaurs, and this extinction basically cleared the stage so that the real dinosaurs could come in and evolve and dominate the Earth. But this extinction event also has some similarities with ongoing climate change. So we'll explore those analogies and also their limits as well. So in this video, we'll examine the largest mass extinction event in Earth history and explain how this was driven by a really big perturbation to the carbon cycle where a whole lot of CO2 was injected into the atmosphere. We'll compare this with ongoing climate change and also ongoing extinction patterns. So what exactly is a mass extinction? I mean, the concept seems simple enough, right? It's all these species becoming extinct around the same time. But identifying this, in the geologic record can be challenging because species are constantly becoming extinct, just as new species are constantly evolving and separating from their ancestors. So one way to do this is by charting the number of marine taxa over time. And so, for instance, this plot here shows the number of marine animal families over the geologic past from basically 600 million years ago till today. So just as a reminder, humans are in the family of the great apes. So that's kind of the resolution, the taxonomic resolution that we're considering here. So around 600 million years ago, there were very, very few animal species, but this went up by a whole lot in the next 100 million years. This is often called the Cambrian explosion. People think this is linked to an uptick of atmospheric oxygen that happened around this time. So more oxygen, you can support multicellular life, and as a result, you get a whole bunch of interesting, weird-looking animals evolve pretty rapidly and start colonizing the Earth. And so you can see this increase in basically biodiversity over time through the Cambrian and over the next several hundred billion years ago. But these steady increases over time are punctuated by some pretty obvious drops here. So this is the first big mass extinction, the Ordovician. There's one again in the Devonian. There's one in the Permian-Triassic boundary that we'll talk about. This is the biggest mass extinction. There's another one at the end Triassic, and then there's the end Cretaceous mass extinction. This is the one that was, they basically killed all the dinosaurs. It's from an asteroid that collided with Earth. But you can see in terms of the scale how kind of unprecedented this Permian-Triassic event is around 250 million years ago. So the Permian-Triassic mass extinction was sort of the end of an era of this Paleozoic biodiversity. A lot of these organisms didn't make it through and were replaced by other organisms throughout the Mesozoic when the dinosaurs dominated, or through the Cenozoic when the age of mammals and modern fish and birds came to prominence. Some of the more notable types here that didn't make it through this extinction event include this helicoprion shark-like fish. So you can see this has this kind of buzzsaw shape for its teeth. This apparently is for cracking really big hard-shelled organisms and eating the soft parts. So they didn't make it through. There are these eurypterids. These kind of, sometimes they're called sea scorpions. These are human-sized, kind of like sleeping bags of doom or something. So they're just going through and being top predators in shallow seas. They didn't make it through. You can kind of look through all of the kind of unusual shapes here. All these organisms were essentially extinct from the Permian-Triassic mass extinction event. And actually, a lot of those that had it worse off were organisms that make shells out of calcium carbonate. So here's a select group of marine species, and you can see their kind of rise and fall throughout this Paleozoic era, through this early mass extinction here, through the Devonian mass extinction. But here, I'll hide myself. There's nothing quite like this Permian-Triassic mass extinction. It's a huge loss of biodiversity. This big red wedge here, these are foraminifera. So the same organisms that survived today to basically tell us what climate was like over the past several hundred million years, they almost didn't make it through this event. So there's pretty similar losses in brachiopods here in purple, crustaceans here in green. There's lots of marine species that were prominent during this time that didn't make it through. So sometimes this event is called the Great Dying, because this is sort of a time when almost all the species on Earth perished, over 90%. So this is a really long time ago. It was 252 million years ago when this event took place. The Earth was really quite different. This is in the middle of Pangaea. And so just to kind of try to spot the continents here that we're familiar with, this is South America right here, Africa. You can see is this landmass over here. This is basically the remnants of North America, or the progenitors of North America, Europe, Siberia. This part actually here is North China, South China. So a very different landscape. India, which is going to collide eventually, is down here. And there's really two big ocean basins. There's Panthalassa, right, which covers basically half of the world. And then there's this body of water called Tethys, which doesn't really exist today. You can argue that some of it is still there in the Mediterranean, but this is a whole sort of enclosed basin around all these island arcs that is essentially unique. So this is what the Earth looked like at 252 million years ago when this kind of catastrophic event happened. It happened really up here in the high Arctic, up in present-day Siberia. And what happened was basically this huge volcanic eruption. This is called the Siberian flood basalts. Just imagine, a ton of magma just coming up to the surface and basically coating, a huge area of Earth with fresh lava. So the Siberian flood basalt eruption, sometimes called the Siberian large igneous province, this started erupting at 252 million years ago. These huge eruptions are thought to be caused by giant mantle plumes that basically sitting at the core mantle boundary, heating up, and then basically sort of melting their way through the mantle on their way out to the lithosphere, melting the crust, and then just creating these huge lava lakes as far as the eye can see. The scale here is nuts. It's like 1,000 kilometers in scope, and so this is much bigger than the analogies that we have today, such as like the Hawaiian hotspot. This is supposedly the scale, so you can kind of see how much bigger the Siberian event is to any kind of modern analog that we have. So this lava comes through, it starts flooding everywhere, and as it does so, all this carbon degasses from basically this mantle material. So carbon dioxide fluxes to the atmosphere go way up compared to normal conditions beforehand. But also as this lava starts spreading out in different directions, sort of finding its way downhill, it finds all this organic carbon in soils. Those get cooked. Those go back to carbon dioxide. Those go back to the atmosphere. It finds all these coal beds from the Carboniferous, right? Those get cooked. Those turn back into carbon. Those go into the atmosphere. Finds some methane deposits. Those go back to the atmosphere. So not only is this eruption providing carbon dioxide just from the carbon that's dissolved in mantle materials, but it's sort of cooking these fossil fuel reservoirs, kind of in a similar analogy to what's going on today. So these flood basalts are still around today. If you go to the Siberia in the Yenisei River Valley, you'll see these canyons cut through basalt like this. And they look a lot like scenes you could find in the Hawaiian Islands, except for the fact that this is in the Arctic and things are cold. But these are basalt. You can see the gentle sloping down here, and then these big canyons cut by the river. And so for a sense of scale here, you can look at this map here. These red dots here are where you have sort of basalt exposed to the surface due to this eruption from 252 million years ago. And then these black lines are sort of the estimated area of impact originally, that a lot of which has been eroded and washed into the ocean. So these are truly massive volcanic eruptions. This is not the only large igneous province that's formed. There's several throughout the world. There's a really prominent one in southern India that actually erupts at the same time that the asteroid that collided with Earth killed the dinosaurs. There's this other group called CAMP, that's the Central Atlantic Magmatic Province. That's located on multiple continents over in Africa and South America and the east coast of the US. This is basically the start of the formation of the Atlantic, the breakup of Pangaea. You can see other ones, Hawaii is on this map, not surprisingly. Iceland is on this map, not surprisingly. There's some other big ones down in the Southern Ocean, like the Kerguelen Plateau. So these are features that happen periodically throughout geologic time. But in this case, in Siberia, they really messed things up. And actually, one of the best known examples of these large igneous provinces, these flood basalts, you can find in the Pacific Northwest. So there's a very large area around Idaho, Western Washington, Oregon, called the Columbia River flood basalts. And if you look at the image behind me, you can see how similar this could look to a scene you might see on Kauai, to that image from Siberia before. These are sort of formed from the same mantle plume mechanisms. These are basalts that are emplaced on land, in this case due to these catastrophic events. And what's kind of interesting is that not all these events lead to mass extinctions. This Columbia River flood basalt, there's no sort of major decline in marine taxa that's corresponding with that. So it has to kind of be at the right place at the right time in order to trigger a mass extinction. And in the case for Siberia, you can see the effect of that sort of cooking of all of that fossil carbon that was around nearby that sort of amplified carbon into the atmosphere. So how much lava are we talking about? So let's start using this log scale. And the units here are in cubic kilometers. So it's kind of easy to brush over that scale, right? If you put your arms out, you can get a sense for what a meter is, right? So if you extend that meter 1,000 times in one direction, that's a kilometer. If you extend that meter, forward from you, and then 1,000 times more forward direction, and then 1,000 meters up, that's the dimensions of a cubic kilometer. It's like crazy big. So the 2018 Kilauea eruption that destroyed tons of property, created new land for the Big Island, that was around 1 cubic kilometer. So that's the scale here. And then, this is all on a log scale. So it's pretty easy to lose perspective here and switch over to a linear scale. So if you added up all the basalt on the Hawaiian Islands, you would basically come to a value around 1 million cubic kilometers. So that's sort of the scale that all the Hawaiian Islands would add up to. The Columbia River flood basalts over in the Pacific Northwest, those are maybe a tiny bit bigger, 1.3 million cubic kilometers. But then when you get to the Central Atlantic magmatic province, that's even bigger. The Siberian traps, or the Siberian flood basalt, those are even bigger. And these Deccan traps, the Deccan flood basalts, are even bigger still. And these three are associated with mass extinctions. What's interesting too is that some of these oceanic emplacements, like the Kerguelen Plateau, or this Ontong Java Plateau in the Western Pacific, these are even more massive. They're off the scale here, but there's no mass extinction associated with them. So again, it seems like the eruption has to be in the right place in order to cause lots of damage. So now we're going to walk through the sequence of events that we think happened in response to this massive eruption and injection of carbon into the atmosphere. So in this top graph here, this black line. This is a reconstruction of carbon emission rates from this event. You can see they start down here. This is sort of the first eruption and placement of lava and the outgassing of CO2. And this spike up here, this corresponds to when all of those fossil fuel carbon reservoirs like coal or soil carbon that was sticking around soils for a long time, those get burned up and released into the atmosphere. And the time scales here are pretty long still though. They're 500,000 years in this direction, 500,000 years in this direction. And the 0 point here, this is called the CIE, the carbon isotope excursion. The details aren't too important, but it's basically when there's a global signal for environmental change and perturbation of the carbon cycle. So this is kind of like an anchoring point here. So you can see this huge carbon spike right at the CIE. And as a result, all this carbon emissions that go into the atmosphere cause atmospheric CO2 to increase. And so from expected values of maybe 500 ppm before this event, things shoot up to maybe 4,000 ppm in its most intense, and then before eventually being consumed away. And this is sort of carbon entering the ocean, then once in the ocean being precipitated as calcium carbonate, being removed from this system. But this is a huge spike in carbon dioxide, that it's a greenhouse gas, and so as a result, you have a huge warming event that lasts for thousands and thousands of years. So these are SSTs that are reconstructed for Tethys Basin here. That's the one between India and Australia and those Asian archipelagos, and then Siberia up north, and then Pentalassa, which covers the whole other side of the globe. If you remember, Tethys was sort of more in the tropics, so it starts out hotter, but both of these basins sort of jump up around 10 degrees in temperature at their peak atmospheric CO2 concentration. So really sort of prolonged global warming in response to this event. All right, but that's not the only effect. So atmospheric CO2 goes up, right? So carbon dissolves in the ocean. So when carbon dissolves in the ocean, you have CO2 reacting with water to form bicarbonate, and that releases this proton that contributes acidity to the ocean. So when we talk about ocean acidification, it's because CO2 from the atmosphere is sort of dissolving into seawater, releasing protons. And as a result, ocean pH declines. So as this line goes through here, remember this is the big release of carbon. There's more protons in seawater now as a result of this event, and it takes a while to recover. And then what happens is that those protons start attacking calcium carbonate. So if you're an organism who's making this shell, it's now under attack from this extra protons here. And that's going to end up dissolving this calcium carbonate and then releasing calcium ions and then bicarbonate here. So as a result, the saturation state of calcium carbonate, basically how easy it is to maintain a calcium carbonate shell, that goes from, all right, to much more difficult all of a sudden during this event, and actually recovers over time, actually due to sort of weathering inputs that are operating on longer time scales. But for a while, you have this kind of really intense acidification event that makes it really hard to keep and maintain your cells. That's one of the reasons why a lot of organisms that have houses of calcium carbonate, that build calcium carbonate shells, why they preferentially went extinct during this event. All right, and then the last major impact from this Permian Triassic mass extinction, this big eruption in Siberia, is ocean deoxygenation. So here's how we think this happened. So we said before that ocean temperatures shot up by around 10 degrees or so. And so that not only makes it hotter for organisms that are dwelling on the surface, but that also leads to more stratification. The warmer sea surface temperatures are, the more there's a density contrast between the upper ocean and the deep ocean. And so it's a lot harder to mix oxygen-rich waters from the surface down into the deep ocean. So you can think about the oxygen supply to the deep sea decreasing a lot. At the same time, there's indications that the biological pump actually benefited from this event. And the thinking behind this is that all of this new lava that got placed in Siberia, it starts to cool, rain falls, it starts to weather, and then all of those nutrients that are in that lava make their way into the ocean and start stimulating biological productivity. And as phytoplankton grow, they sink, and their biomass basically enters the deep ocean, and then the bacteria living there consume oxygen in order to respire it, right, to turn it back to CO2. So you have less oxygen supply due to stratification, you have more oxygen demand from more sinking material entering the deep ocean. And as a result, oxygen concentrations go way down in the subsurface. So these lines represent different depth strata. Basically, in the surface ocean, you only see a really small change in dissolved oxygen, because you're always sort of resupplying from the atmosphere, and then you're making a lot with the biological pump. But in the deep sea and intermediate waters, you see this huge crash. And so you basically go to oxygen levels that a lot of organisms can't grow in anymore. So this is another major sort of kill mechanism for a lot of the species that died in the Permian Triassic mass extinction. So in the end, we have these multiple stressors that are contributing to the demise of the organisms 252 million years ago. These are, so there's ocean acidification, there's warming, there's oxygen loss. All of this is sort of adding it up to make it really difficult to survive under these conditions. And actually, there's some indication that if you lived around the equator before, you were actually more capable of tolerating this, or at least not all the species went extinct. It's thought that you had high temperatures around the equator already. Maybe you had some tolerance to low oxygen already. But a lot of the organisms growing in the poles, they really suffered, and extinction rates were extremely high here. All right, so as a final comparison, let's compare this sort of magnitude of global change to what we're experiencing today. So the Permian Triassic, as we mentioned before, all that release of CO2 led to an increase in temperatures of around 10 degrees C at the sea surface. So that's a pretty huge change. You add up all the climate change that we've experienced today, we're around 1 degrees warming from pre-industrial times. Depending on the different emission scenarios, we could see anywhere from 2 to maybe 8 at the really high end degrees C of warming by, let's say, 2200, so the next 2 centuries. So the Permian Triassic was, a much greater magnitude perturbation. If you look at the acidification that happened due to this event, pH went from a background of around 8.1 and then became more acidic to around 7.6. That's a 3 or 4 times increase in protons available to sort of attack calcium carbonate shells. What we've seen so far today is it dropped from 8.2 to 8.1, which is a fair increase already, and it may keep going to 8.0 or 7.7 in the really high emission scenario. So there's still a risk of ocean acidification, but not as intense as this event. So as far as ocean deoxygenation goes, there's lots of evidence that this Permian Triassic event led to global scale anoxia. And this is a big mechanism that sort of led to fish and other organisms that breathe oxygen becoming extinct. Now what we're seeing over the past few decades is that there's a slow and steady drop in oxygen inside the ocean's interior. And this is due to this ocean stratification mechanism where, because the surface of the ocean is warming, there's less exchange with the ocean interior. But the size of this trend is nowhere near the same as during this mass extinction. It's pretty unlikely that the oceans will become anoxic or basically impossible. But there are some regions of the oceans that are lower in oxygen naturally, and those might become sort of more severe and may exclude certain species in the future. So overall, the main stressors that led to this massive extinction, they're a lot less intense than the climate change that we're experiencing today. And that's really because the amount of CO2 that was released during this eruption, 106,000 gigatons, is a lot less than what humans have put in the atmosphere so far. We're at around 665 gigatons. I think that's a 2020 number. Yeah, so the magnitude of perturbation is a lot less intense. So this is one of the reasons why some of these mass extinction events, although the mechanisms are similar, they're not perfect analogies. You could add a whole lot of other caveats to this. Continents aren't arranged in the same way, so you'd expect the Earth system to respond differently. The organisms that are growing are different, so they may be more tolerant of different conditions. But if you think about the rate of carbon release over this 100,000 year event, you're sort of looking at peak values of around 0.7 gigatons of carbon per year. But today, or at least over the past few years, the release rate has been around 9.6 gigatons of carbon per year. So we're actually, in a velocity sense, we're beating this huge mass extinction. We just haven't been putting carbon in the atmosphere for as long. So that's a bit of a kind of a dire warning, but it's also a sign that we can turn back if we change our ways. And so you may have seen some speculation or some commentary about humans potentially starting the sixth mass extinction through accelerating habitat loss or hunting, poaching, overfishing, anything that can lead to the extinction of species, and that this is on the same level as these major mass extinctions in the past. That's probably not totally accurate. So here's a comparison I found that basically counts all of the mammals that have been extinct. This axis here is basically a percent. So basically it says that around 1% of all mammals have gone extinct in the last 500 years due to human activity. But if you count the species that are currently threatened or endangered as doomed here, then this may be up to 22%. Similarly, for birds, there's around 1% confirmed extinct, 14% that are threatened and may become extinct if we don't get our act together. So even though some of these these percentages are high and very concerning, they're nowhere near the magnitude of the big five mass extinctions. In all of these cases, it seems like over 75% of species died out because of these events. Now, there's some caveats here. You can only really tell who went extinct based on who made fossils beforehand. So it's potential we're missing some species, not counting them, but still there seems to be a pretty big departure. This here is the Permian Triassic mass extinction, where almost 100% of things died. Life only sort of barely squeaked by. And so these extinction rates are kind of like the situation for carbon. We haven't put nearly as much carbon in the atmosphere as occurred in some of these mass extinction events like the Permian Triassic. But we're still putting carbon into the atmosphere at a huge rate that exceeds these events. And actually, if you consider species extinction rate here, these are sort of on the same level as some of these major mass extinctions in the past. So extinction of birds, of mammals, of amphibians, if you consider the endangered and threatened species as inevitably extinct, then we're sort of at the level inferred from the Cretaceous extinction where things died out really fast, right, because the asteroid just slammed in. This Permian extinction here is down here. So we're losing species at a really fast rate. The only difference is that these events happen for thousands to millions of years, whereas we've only been really doing this kind of full-heartedly for the past 100, 200 years. So to some extent, this is kind of a really dire warning, but there's also a lot of hope here in that we can change our ways. We can get our act together, we can conserve animals, we can stop emitting carbon, and we can avoid some of these these worst episodes in human history repeating themselves. All right, so we've gone through the Permian Triassic mass extinction, the largest mass extinction in Earth's history. This was basically due to this huge eruption, this almost unprecedented scale eruption in Siberia that led to millions of cubic kilometers of lava coming in, pushing all this carbon into the atmosphere, and then adding a lot more because that lava basically, as it flowed through the landscape, burned up soil carbon and fossil fuel carbon reservoirs. And then that led to warming of the atmosphere that led to deoxygenation of the ocean, and it led to ocean acidification. These multiple stressors seem to combine to really kind of devastate a lot of the calcium carbonate shelled organisms and a lot of the organisms that feed on them, like those kind of buzzsaw sharks. So the mechanisms here are really kind of quite similar to what's going on with modern climate change, but the magnitudes aren't the same. There's so much more carbon released in the Permian Triassic extinction than we're releasing today. But the rates of carbon release and the rates of extinction of species are actually quite high. So if these keep going, then we could reach these kind of geologic scale magnitudes.